Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture we will continue our discussions on density functional theory. So just as a recap of what we did in the last lecture, we looked at a set of exchange correlation functionals including semi-local, LDA, GGA and meta GGA. And then we also looked at hybrid functionals as a way to include non-local interactions and DFT plus U to mitigate your self interaction errors, right. So different functionals have different strengths and weaknesses, so always think about whether they are overbinding or underbinding, how much derivative discontinuity they have and what kind of computational expense they will incur. And in this lecture we will also look at some of the additional approximations that are there within DFT and go towards more practical aspects of how you actually do a DFT calculation. Okay. So what are some of the practical considerations, right. So the first is what is your system. So is it a periodic system or is it a non-periodic system. So generally solids are periodic and molecules are non-periodic. So depending on your system itself you may have to choose a basis set accordingly, for example, right. So basis set is how you are expanding your one electron wave functions, right, within your Kohn-Sham framework. So we are representing our electron densities as a summation of one electron wave functions, and these one electron wave functions are in turn expanded on some orthonormal basis set. So what is the basis set that we use, that is something that we need to consider, and how do we converge this basis set. So how do we know that our basis set is good enough and are we sampling the basis set well enough. So let us say we are using some kind of sampling techniques or mesh techniques to sample our electron densities at different points in space. Are we sampling the electron densities at a sufficient number of points, right. So these are again some practical considerations. And then there is also this aspect of pseudo potential. So we will get to what these pseudo potentials are and what are some of the design choices that we need to make in terms of pseudo potentials, and when do we consider our calculation to be good enough, right. So whether we only converge on energy or we also look at forces, right, and how many degrees of freedom do we provide our system as it tries to reach its ground state, right. So do we only allow the electrons to reach their ground state, or do we also move the ions, right, and allow the system to reach its ground state. And these are all practical considerations apart from the choice of functional itself, right. So think of these practical considerations as equivalent to hyperparameters or design choices that you typically have in your machine learning models, right. So in machine learning models you have several design choices. So how many convolutional layers you have, what kind of pooling mechanism you choose and so on, and you also have hyperparameters, right. So what is your learning rate, how many epochs you use, what is the batch size and so on, right. So those are all your hyperparameters. These basically represent your hyperparameters or design choices that you have when you do a typical density functional theory based calculation. So let us look at some of them in little more detail. So with respect to basis set itself, right. So if you have a non-periodic system, so this is an example of a caffeine molecule that is found in coffee, right. So if you have a non-periodic system you use typically a localized basis function, and there are several different choices that you can make when you have a localized basis. Simplest one is a collection of Gaussians. So each orbital you basically represent as a collection of Gaussians or as an expansion of Gaussians. So these Gaussians sort of superimpose on one another, and you basically use that to represent electrons in a fairly localized state, right. So you typically use a localized basis in a non-periodic system, but if you have periodic systems such as, so this is a simple illustration of a sodium chloride crystal structure, the basis set of choice is typically plane waves. And the reason for that is in periodic systems you need to take into account what is referred to as the periodicity of the lattice, which is formulated in Bloch theorem, right. So what Bloch theorem basically states is that if you have a periodic lattice, right, so a lattice that repeats itself in 3 dimensions, basically your charge density has to be identical at equivalent points in space, right. So let us say you take in a sodium atom here and you calculate a charge density associated with the sodium atom, if you take a symmetrically equivalent sodium atom, right, in the next unit cell, the charge density here should be identical to the charge density here. If it is not identical, then the system does not have translational symmetry, because in a solid, whether I draw a unit cell here or whether I draw a unit cell here, I should have the same properties, right? I should have the same bond length, I should have the same lattice parameters, I should have the same thermodynamic properties and so on, right? That is how solid systems or periodic systems behave, right? And this should translate to charge densities also. So charge densities that you calculate here should be identical to the charge densities that you calculate here, right? So if this condition were to be satisfied, so if charge densities have to obey translational symmetry, then the underlying wave function also needs to have translational symmetry, right? And Bloch theorem basically tells you how these wave functions should look like. So if a wave function has translational symmetry, how should it look like? What kind of functional form should it have, right? And in contrast, so if you just think about a simple hydrogen atom, right, which can be analytically solved, here the wave function has spherical symmetry, right? So in contrast to hydrogen, in periodic solids your wave function should have translational symmetry, and one of the basis sets that have this translational symmetry are basically your plane waves, right. So plane waves are guaranteed to have this translational symmetry because because of how periodic they are. So what are plane waves? Plane waves are basically a collection of sines and cosines. So whenever you cross a period in a plane wave, right, you always recover back the same value, right, and as long as you choose the period to be some kind of a multiple or associated with your bond lengths or with your unit cell dimensions, right, the plane wave will repeat itself, right, in its periodic image as well. So plane waves intrinsically have sort of translational symmetry, and those form a natural set of basis functions whenever you have periodic lattices, right. And the nice thing about plane waves is that you can very easily perform Fourier transforms. So in other words, you can go from sampling your wave functions or your charge densities from real space to reciprocal space very easily. So real to reciprocal space is just a Fourier transform, right, of one another. So from real space, if you do a Fourier transform, you go to reciprocal space, and if you do an inverse Fourier transform, you come back to real space. So let us say you have a bunch of plane waves that are representing your wave function and hence your charge density. You can now sample your wave function or your plane waves in either the real space, or you can do a Fourier transform and go into reciprocal space. The nice thing about reciprocal space is that it is a very nice mathematical framework to model long range interactions, right, and basically deal with infinities. So in reciprocal space, atoms that are far from one another are basically closer, right, and atoms that are actually close by are actually far apart in reciprocal space, right. So reciprocal space provides us a nice way to capture in fairly long range interactions, right. Since we so in most practical settings, so whenever we use periodic systems, we use plane waves to represent these periodic systems, and we almost always split the sampling of our charge density into real space as well as reciprocal space. So for interactions with nearest neighbors, so for example for this sodium interacting with its nearby chlorine atoms, we model these or sample these interactions in real space. But if sodium were to look at one of its periodic images, right, then we sample those interactions in reciprocal space, right. So since we split the sampling into real and reciprocal space, the subsequent question is how do we sample this reciprocal space itself, right, and this is where the aspect of k points come in. So the simple way to think of k points is the kind of mesh you use to sample your reciprocal space. So just like you can construct a fairly symmetric, let's say in the case of sodium chloride structure, this is a cubic structure. So you can construct a cubic mesh to sample your real space, right. So just like you can construct a cubic mesh to sample the wave functions at discrete points in your real space, you can do the same thing. So when you transfer the problem into reciprocal space, you can also construct a mesh to sample your reciprocal space, right. And this mesh is basically referred to as a collection of k points, right. And the denser the meshes, the more computationally expensive your calculation is, but also more accurate your calculation is, right. So k points now becomes a very important hyperparameter to optimize whenever you do calculations on periodic systems with plane wave basis. Okay. So let us think about how to converge our basis set itself. So in periodic systems, we are using or we are expanding our wave functions, one electron wave functions as a form of plane waves, right. So plane waves basically represents our basis set and we need to converge our basis set, right. So in principle if we use an infinite basis set, so if we use infinite number of plane waves we can represent our exact one electron wave function, right. But we cannot use infinities because we do not have so much computational power and we cannot deal with infinities that easily, which implies we need to use some kind of a cutoff criterion or a convergence criterion and identify up to how many plane waves do we actually use to represent our one electron wave function, right, and that kind of convergence we need to do, right. So to give an analogy to classical machine learning models, right, so think of this as hyperparameter optimization, right. So you need to optimize these hyperparameters to ensure that your calculations are accurate enough but at the same time computationally tractable, right. So how do we converge our basis set? Usually we do these convergence based on total energy predictions. So we keep calculating the total energies as a function of different basis set sizes, right, and as long as the total energies do not vary beyond a certain tolerance, right, we consider that value of our basis set to be converged, right. So the tolerance that is typically given for solid systems is about 10 to the power negative 5 electron volts. This can be per cell that you are considering or this can be normalized per atoms, right, that you are considering. So the tolerance is again a design choice. There are researchers who like to have very low tolerances, so that can be like the researchers who like to have very high tolerances, so that can be 10 to the power negative 6, negative 7 and so on, and researchers who like to have fairly low tolerances, that can be 10 to the power negative 3, negative 2 and so on, right. So the tolerance that you use may also depend on the problem at hand, right. But generally the one sort of advice is to always use tolerances that are 10 to the power negative 5 eV or lower, so that you are very much close to the noise level of your actual DFT calculation, right. So the convergence of the basis set is usually done on total energy predictions and this is irrespective of whatever basis set you use. So even for non-periodic systems, if you are using a bunch of Gaussians, you would use total energy predictions to determine whether your basis set has converged or not. So for plane waves per se, we only have to define some kind of an energy cutoff, right. So in the case of plane waves, so energy is equivalent to frequencies or wavelengths of your plane wave itself, right. So the higher the energy, the higher the frequency or the more wiggly your plane wave is. So the lower the energy or the lower the frequency, the higher the wavelength and hence the more smooth your plane wave is, right. So as you keep increasing the energy or increasing the plane waves, your wavelength sort of shorten and the more wiggly your plane wave actually becomes, right, the more oscillating it actually becomes. So generally the way we define a plane wave basis set is that you basically define an energy cutoff. So you say up to this energy, so from let us say very close to 0 all the way up to this energy, you use plane waves to represent your wave functions, right. So up to this energy or a maximum or equivalently a maximum frequency, right. So in general when you have higher and higher energy cutoffs, the more plane waves you actually include to represent your underlying wave function, and you are using variational principle, you are guaranteed to get lower energies, right, because you are getting closer and closer to the true representation of your wave function, the more of your basis set you actually include, right, and hence you are guaranteed to have lower and lower energies. But at the same time your calculations are going to be computationally more expensive, right. So higher the energy cutoffs, more accurate your calculations are, but more expensive they are, right? Another thing to keep in mind is that the convergence of the basis set is also dependent on on how you are sampling them in reciprocal space. So if you are sampling your basis set in a very coarse manner in reciprocal space, then the convergence may not be smooth. So in other words, you may not reach this tolerance as well as you should be, right. So you may have some oscillations here and there. So the basis set itself can also depend on the choice of the exchange correlation functional also. So different functionals may require different amounts of basis sets, so different energy cutoffs, so that they are able to make their predictions accurately. They are able to make their total energy predictions accurately. So in general, for example, the meta GGA functions such as scan require higher energy cutoffs typically, because they have to include in the second derivative information or the curvature information. Scan does it through kinetic energy densities. So since it has to represent kinetic energy densities also, it requires generally higher energy cutoffs compared to, let's say, an LDA, where the exchange correlation functional is only a functional of the density at a given point. So in general, if you are only representing the function at a given point, then you require fewer number of parameters to numerically represent that function. If you want to represent the gradients also, you require more parameters. If you want to represent the curvature, the Laplacian, you require even more parameters. So in general, as you go from LDA to GGA to meta GGA, you will require a larger basis set to reach the required convergence, right? And in general, so for us to do this convergence test, right, so we almost always insist on choosing a dense enough k-point grid. So you choose a grid of sampling a reciprocal space as dense as possible, and then you do a convergence on your basis set. And once your basis set is actually converged, then you do a convergence on your k-point grid. And this is because if you use a dense enough k-point grid, and if you if you use a dense enough k-point grid, you are sort of guaranteed that you are sampling your reciprocal space fairly well. So you won't have this oscillating behavior with respect to energy as a function of your basis set size. So the larger your basis set is, the lower your energy is going to be. So you are going to have a smooth decay of energies as a function of basis set size, right, decay of energy differences as a function of basis set size, and hence you will reach your tolerance, or you will identify at what basis set size you will reach your tolerance much more accurately, right, if you use a dense enough k-point mesh. So idea is to first converge on the basis set size and then use the converged basis set size to then converge your k-point grid, or how dense you are actually sampling your reciprocal space. And this is because so k-point meshes at the end of the day are just a way to sample your reciprocal space. So they do not always guarantee that the denser you go, the lower your energy is going to be. So they do not obey the variational principle in that sense, because they are only a numerical sampling. And hence you'll almost always have a non-monotonic variation of how your energy is actually varying with respect to your k-point mesh, whereas with respect to basis set size you will have a smoother variation, right. So try to always converge your basis set size first and then your k-point grid. Okay. The other important aspect to note when you do density function theory calculations is the idea of pseudo potentials, right. So the main sort of thing to note is that when you think about any atom or any system, right, it has a set of core electrons and it has a set of valence electrons. So if you take the case of iron, for example, so iron has 26 electrons in total, right, 18 of them are core electrons. So up to the argon shell, the 3p shell, everything is core electron, and the valence electrons are basically it's 4s2 and 3d6, it's 8 electrons are valence electrons, right. And whenever iron forms a chemical bond, right, with any other species, only the valence electrons are involved and the core electrons are almost always not perturbed, right. So they do not really participate in bonding, which implies that the core electrons are not really relevant as long as we are interested in modeling how chemical species bond, right, in a given system. So if we find a way to model these core electrons, sort of using some kind of an effective potential, we can actually reduce the computational cost, right. So what do I mean by that? So if you look at how the valence electrons actually, or what the valence electrons actually experience in a given system, they only experience an effective potential, right. So the valence electrons usually do not see the nucleus, the positive charge in the nucleus directly. They see a screened charge of the nucleus, where the screening comes in from the core electrons. So the 8 valence electrons of iron do not see the 26 protons directly. They actually see 26 protons that are screened by 18 core electrons, right. So they see some kind of an effective potential. So if you now mimic all the core electrons with this effective potential, right, you can basically reduce your computational task from modeling all of these 26 electrons explicitly to modeling only the 8 valence electrons, right. So this is the basic idea behind the construction of pseudo potentials, right. So pseudo potentials are primarily designed to reduce the total computational cost. So they basically reduce the total number of electrons you are explicitly modeling in your DFT calculation. So you do not model the core electrons explicitly, you model only the valence electrons explicitly, and hence you reduce the total number of electrons to be modeled, and hence you lower your computational cost, right. But having said that, whenever you use a pseudo potential, you are guaranteed to have a lower accuracy than an all electron calculation, right. And this is simply because you are reducing the number of degrees of freedom that are available for your system, right. So initially your system had 26 electrons that it can distribute the way it wants, your ion atom. Now it only has 8 electrons that it can distribute the way it wants, right. So you are reducing the number of degrees of freedom that your ion atom has, and hence if you are reducing the number of degrees of freedom, the ability for you to reach your true ground state wave function is lower compared to what you had before, and hence just using variational principle we will have lower accuracy compared to an all electron calculation where you model all the electrons explicitly. And pseudo potentials can also break down under select circumstances, especially when you have very short interatomic distances or bond lengths under especially high pressure scenarios, or if you have atoms that are moving very rapidly under very high temperature scenarios, your pseudo potentials can also break down under those circumstances. So how are pseudo potentials constructed? So the sort of qualitative way to understand is they try to minimize some kind of a loss. So the loss could be in terms of energy predictions, and the loss could also be in terms of what kind of potential your valence electrons actually observe beyond a certain distance from your nucleus. So pseudo potentials are constructed by minimizing some kind of a loss against an all electron calculation. So you do a reference all electron calculation once, and then you construct a pseudo potential that sort of mimics the all electron calculation, and then you use the pseudo potential moving forward. Just to note that pseudo potentials actually have a lot of nice illustrations in this Wikipedia page itself, right. The write up is also quite nice. So if you are curious as to how pseudo potentials are constructed, what kind of losses are minimized, I sort of highly encourage you to go to this Wikipedia page. They also have some very nice illustrations, right. So just briefly enough, originally you had a bunch of nuclei and then you have the individual electrons, right, that were interacting with the nuclei directly. When you construct a pseudo potential, this nucleus is completely screened. So your valence electrons here basically interact with what is referred to as an effective core, which has a nuclei plus core electrons, right. So the interactions are a little bit different. So pseudo potentials are a purely mathematical construction. They are designed to reduce our computational load when we do a typical DFT calculation, and since they are a purely mathematical construction, there are a whole zoo of them, right. The first ones are the sort of what are referred to as empirical pseudo potentials. So here you simply cut out the core itself and then insert a simple Coulombic repulsion term, where the Coulombic repulsion term comes in with its with the effective charge. So in the case of iron, if you cut out the core of 26 nuclei and 18 core electrons, the effective charge you have is about 8 positive charges, right. So you sort of insert an effective Coulombic term, so you have an attractive term and a repulsion term that sort of acts on your valence electron. So these are sort of empirical in nature, and the way these the effective Coulombic terms sort of interact with the valence electrons are usually fit on some kind of derived properties, and these empirical pseudo potentials are in the modern era they are no longer used because they are not very transferable. They also affects how your what kind of expansions you can get from your wave function. So they really are dependent on the basis set. So empirical pseudo potentials were used way back in the past, but in the modern era they are not used. In the modern era, these three potentials are still used. Out of these, norm conserving is the sort of most oldest in terms of its formulation, and it's also it can be a little bit more computationally heavy. So the main sort of idea behind norm conserving pseudo potentials is that it uses Gauss's law. So Gauss's law states that when you have a sphere, right, a spherical distribution of charges, it doesn't matter how the charges are actually distributed within the sphere, all the charges outside the sphere only see an effective charge, right. So it basically uses that principle. So what it does is valence electrons experience some kind of a smooth distribution of charges inside the core. So normally you would have a wild oscillation of charges within the core depending on where the core electrons are localizing. So you remove all those oscillations and replace that with a smooth function here. Of course you conserve the total amount of charge inside the core radius. The basis set is chosen depending on which orbitals you plan to fluidize. So which orbitals are put in the core shell, and there are also different types of norm conserving pseudopotential. So the hard ones are typically accurate, but they are also computationally expensive. The soft ones are not that accurate, and in general the harder ones are more transferable compared to the softer ones, right, because they because they are more accurate, right. So that is norm conserving pseudopotential. The ultra soft pseudopotential basically aims to reduce the computational load compared to the norm conserving pseudopotential. So it reduces basis set size, it relaxes the norm conservation rule. So it relaxes this rule that the total number of charges has to be conserved. So it sort of compensates this by introducing some kind of augmentation charges, right. So I will not go into the details, but basically it tries to reduce some constraints in how you construct the norm conserving pseudopotential so that you are computationally quicker, right. And the basis set, the nice thing about ultra soft pseudopotentials is that the basis set is independent of species. So it can be more uniform and it is computationally faster, and unfortunately the information on all the core electrons are lost, and usually the ultra soft potentials, the modern ones work only with plane waves, right. So in our hands-on exercise on doing a simple DFT calculation, we will use an ultra soft potential because it is computationally quick and you can actually reproduce the calculations on a simple laptop well enough. However, the state of the art in terms of pseudopotential construction is actually these projected augmented wave potentials. They actually retain all the information of the core electrons, but do not increase computational cost significantly. So they use what are referred to as projection operations to obtain information from the core electrons basically, and these are transferable, fairly efficient, and works well with plane waves. The only problem with projector augmented wave potentials is that these are difficult to construct, and hence there are very few developers out there who have constructed reliable projector augmented wave potentials, right. But for our hands-on exercise we will use ultra soft potentials. Okay. The other important thing, important design choice to keep in mind when it comes to DFT calculation is how many degrees of freedom you give your system. For example, when you do a DFT calculation, right, are you only allowing the electrons to be relaxed, so you are considering the structure to be static, or do you also consider ions to move? If ions can move, so should you keep your box, your lattice parameters the same, or should you also change your lattice parameters? What about shape of the box? So you can have the same volume, but you can go from a cubic system to let's say a hexagonal system or an orthorhombic system, right, or even a monoclinic system, right. So you can keep the same volume, but you can change the shape, right. So what degrees of freedom do you typically give in your system? So these are again design choices. So it depends on the problem and the system at hand, right. The other thing that you can also think about is whether you want to preserve symmetry, right, in your system. So during the course of a calculation, especially if you want ions to move, if you want volume to change, if you want shape to change, should you preserve your symmetry or not, right. So if you do not preserve your symmetry, you can even have a transition from cubic to triclinic, right. So cubic is cubic is the highest form of symmetry that we have in our crystal systems. So all the three sides are all the three edges are equal and all the three angles are equal. Triclinic, none of them are equal. So all the three sides are different, all the three angles are different, right. This kind of a transition will become possible if you do not preserve symmetry, right. But this is something that maybe you have to consider for your system. You have to give it the degree of freedom to see if the system wants to go away from a cubic structure to a triclinic structure. And in general, if you preserve the symmetry, you generally tend to reduce your k-point sampling, because the k-point sampling depends on your reciprocal space and how you represent your system in your reciprocal space. We use something called an irreducible Brillouin zone representation of our crystal structure, and this Brillouin zone representation changes depending on the underlying crystal structure itself. So cubic structures have different representation of your Brillouin zone compared to triclinic structures, and since cubic structures have more symmetry, their Brillouin zone representations also have higher symmetry compared to your triclinic cases, which implies you will need fewer or less dense meshes to sample your cubic system compared to your triclinic system. So in general, if you preserve your symmetry, you can tend to reduce your k-point sampling, but this is again once again depends on whether you are preserving your symmetry or not. But let us say your system has symmetry breaking ground states. So this is especially important for perovskite systems, piezoelectric systems and so on, and even magnetic systems, right. So if you have systems that actually break the symmetry to reach their ground state, then you have to break your symmetry, right. You cannot preserve your symmetry and expect you to reach the right ground state. Okay. So one of the typical calculations that you would do when you start off with DFT with the density function theory is do a structure relaxation. So in structure relaxations, you decouple your ionic and electronic motion using Born-Oppenheimer approximation. You relax your electrons using the self-consistent loop, and then you relax your ions using classical dynamics, right. So typically in a structure relaxation, you allow your ions to move, your shape to change, and your volume to change as well. Typically you do not preserve your symmetry to see how the system is behaving without any constraints. So you do not constrain your system, and if your system continues to remain, let us say, cubic, so you started off with cubic, it remains as cubic, then you have high degree of confidence that cubic structure is your ground state, right. And when we do a structure relaxation, the resultant structure and the resultant electron density and the resultant energy basically constitute our ground state of our system, at least as per DFT. So whatever approximations we have used in our DFT, as per those approximations, that is the ground state representation of our system. So in our structural relaxation, we typically have to use some kind of converged basis and converged k-point grid. So the convergence tests have to be made before we do a structural relaxation. Use a reliable pseudo potential, rely on literature or do your own tests, right, to identify the pseudo potential. Have a reasonable choice of exchange correlation functional, right. So for metals, don't use hybrid functionals, and if electronic structure is important, use hybrid functionals, or at least a Hubbard-U corrected functional. Do not preserve symmetry, as I mentioned before. When you start off with the structure, do not preserve symmetry, see what the structural relaxation actually gives you. So try to provide as high degrees of freedom as possible and see if you recover back the same structure that you started with, right. And then typically when you do convergence of your calculation, you converge electrons on energy, so you converge electron density itself on the energy, but the ionic motion you converge on forces. So ideally in a true ground state structure, the ions won't have any forces acting on them, right, and the electrons would have converged to their lowest possible energy as possible, to an energy state that is very close to their ground state as possible. And try to use tight tolerances for both the energies. So electrons converge on energies, so and then ions converge on forces. So try to use tight tolerances, and always try to relax your structure twice. So let's say you start off your structure, it relaxed to your ground state, your calculation actually ended. Try to start a calculation with that relaxed state and see if you recover back the same structure, right. So try to always relax twice, because this can help you break any local minima. So let's say during your calculation your structure actually converges to a local minima. If you restart a calculation from the structure, you can try to break away from the local minima and reach a global minimum, right. And most important to doing a structure relaxation is basically your starting structure. So ensure that the starting structure is actually good, ensure that there are no overlapping atoms, so two atoms do not sit on the same position in your structure, and all sites are fully occupied. So there should be, so DFT cannot model partially occupied sites, so all sites should be fully occupied. So either they are fully occupied or not occupied at all, right. So that's how DFT can actually model. So make sure that there are no overlapping atoms, no partially occupied sites and so on. Okay. So in terms of actually doing a bunch of calculations, there are again a whole zoo of packages that are available. So you don't have to write a DFT code from scratch, you can use one of these packages. Quantum Espresso and WASP are the most popular ones for solids. Quantum Espresso is open source, which is what we will be using in our hands-on exercise. WASP is proprietary, so you will have to obtain a license, and there are a whole suite of other codes available. Some of them are open source, some of them are licensed or proprietary, and each package has its own strengths and weaknesses, and there are also biases that come in from existing users. So make an evaluation of those strengths and biases and see which package you want to use. But a good place to always start with is, if you do not have a license, start with Quantum Espresso. If you have a WASP license, start with WASP. Right. So we will take a brief recap, and then I'll summarize the DFT lecture as or the set of lectures on DFT as a whole. So a recap of this lecture. So we looked at some of the practical constraints while running DFT. So these are similar to hyperparameter choices in machine learning, and some of the choices that we looked at were basis set choices, pseudo potential, degree of freedom, convergence criteria, choice of exchange correlation functionals, and so on. And for solids with periodic boundary conditions, the basis set that we almost always use is plane waves, where we split our calculations into real and reciprocal space. We use pseudo potentials to increase computational efficiency. There is of course some cost on accuracy. State of the art is projector augmented wave potentials. We will use ultrasoft potentials in our hands-on exercise, and structure relaxation is the typical DFT calculation that you would do, and whatever properties that you are after, you can get them after a structure relaxation calculation. And just to give a glimpse of what you would see in your hands-on exercise, so this is how a typical input file in your Quantum Espresso will look like, but we will be using this atomic simulation environment for doing our calculations. So there you will have to indicate your input variables, input settings through this kind of a code block here, and we will be doing an exercise on calculating the band gap of nickel oxide. So this is sort of the output that you should be getting after the calculation. With that, let us summarize our series of lectures on density function theory. So we see that first principles calculations basically provide the data, the fuel for training most modern machine learning models. So they combine the Schrodinger equation with 4 principles. So the Born-Oppenheimer approximation, the Pauli's exclusion principle, Hohenberg-Kohn theorems, and also the variational principle, right? And DFT is quite a powerful tool. It can compute several types of properties as well. And then we looked at Hartree-Fock as a way to as the base of quantum chemistry calculations, and it's quite relevant till now. And then DFT itself basically goes away from quantum chemistry calculations by modifying the Hamiltonian, by establishing this relationship between the external potential, the energy, and the ground state electron density. And DFT achieves cubic computational scaling, and it has become quite popular for modeling solids. The key unknown is the exchange correlation, right. So there is a whole zoo of exchange correlation functionals, a whole zoo of pseudo potentials, and a whole zoo of packages that implement different pseudo potentials, different exchange correlations, and also basis sets, right. So be careful in choosing your choice of exchange correlation functional, choice of pseudo potential, and choice of package as well. And we have given several rules of thumb, but if you look at the literature, some can be highly opinionated, some can also be rich and confusing, but it's always almost always good to follow some rules of thumbs, at least rules of thumb at those that have been listed in this in this series of lectures. And then ask an expert for advice. That is almost always a good place to start with if you are doing DFT calculations. So with that, we are done with density function theory. In the next lecture, we will continue with exploring other physics based modeling or simulation techniques such as molecular dynamics, and we will continue going towards this physics based calculations a little bit further in the next parts of this course. So with that, I thank you all for joining today's lecture. I will see you all in the next one.